Flipped classroom video for Maths AS Unit 1, Finding Stationary Points. So we'll first have a look at the types of stationary points. We have a maximum point at A. This is strictly a local maximum because if we look at the graph across where x goes up from 0.5, then off the picture we can see that it goes above the y value of A, so it's locally a maximum. And we notice that the function decreases either side of it, hence local maximum. At B we have a minimum point. Again, this is strictly a local minimum. We can see that the graph goes lower when we go further negative than -3, and the function increases either side of this point. Both of these points are called turning points. Maximums and minimums are called turning points because the graph is for a maximum going up and then back down again, so it turns, and vice versa for a minimum. We also have point C, which is called a stationary point of inflection, and the function decreases to one side of it, so if we move towards the negative, the function goes down from C, and it increases the other side, so if we move towards the positive, then the function increases. Another way of saying that is as we approach the point which is the stationary point of inflection from the left, the function is increasing. It stops increasing at the point but then carries on increasing, and of course that can happen the other way round, as it were. So the function can be decreasing on its way to the stationary point of inflection from the left and then carries on decreasing after the stationary point of inflection. For all of these, the curve has a gradient of 0 at the stationary point, and we can see that because the tangents drawn to each point are flat, i.e. they have a 0 gradient. Incidentally, you will look at points of inflection in more detail in Maths A2. There's quite a bit more to them. So we know that at a stationary point the curve has a gradient of 0, and that's equivalent to saying that a stationary point on a curve has dy by dx equal to 0. And therefore, if we want to find a stationary point, we need to find what values of x dy by dx gives us 0. So we'll have a look at an example. Find the stationary points for y equals 2x cubed minus 3x squared minus 12x plus 5. The first step is to find out what dy by dx is. So we have to differentiate the function. So 2x cubed becomes 2 times 3x squared, minus 3x squared becomes minus 3 times 2x, minus 12x becomes minus 12, and if we differentiate plus 5 we get 0. So tidying up, dy by dx is 6x squared minus 6x minus 12. Step 2, we need to find out when it is that dy by dx is 0. So we can put this expression equal to 0, divide through by 6, and then this one factorises nicely, and therefore we can find that x is either minus 1 or x equals 2. So we know that we have stationary points when x is minus 1 and when x is 2. So the next step is to find the y value for those points. To do this, we just put the values back into the function. So when x is minus 1, y is 2 times minus 1 cubed, minus 3 times minus 1 squared, minus 12 times minus 1, plus 5. You can just enter that straight into your calculator if you like. I'm just running through the calculation. Makes it easier to check afterwards that we haven't made a slip with our pluses or minuses. that sort of thing. But anyway, we end up with y equals 12. When x is 2, we do the same process. We put it into the function, work out what each bit is, tidy up, and we end up with y is equal to minus 15. So that means from that step we now know that we have stationary points at minus 112 and 2 minus 15. We can have a look at that here, so we can see from the graph what the nature of these points is, but how can we find that out if we don't have a graph? Obviously this graph was made with dynamic software, GeoGebra in this case, but you won't always have that available, so we need to know how to find out whether these points are maximums, minimums, or stationary points of inflection. We can of course sketch graphs, so that's a way of doing it, but do we have a way of doing it without a graph at all? And just a last thing here, notice that the graph has different scales on the axes here, in case that was concerning you.